Hi, NorthSec. My name is Dimitry Snezhkov, and I work at X4Shred at IBM. I do security work, and this talk is something that we came up with for the past probably half a year, is that we are going to try to retool with .NET payloads on-site at the customer. So the problem of a red team operator once you get on the host is that you have a first mover disadvantage, right? What does that mean? That means that you have to move first to be able to discover what the system is, how it operates. Essentially, you need to do your recon first. And you may be stopped by a lot of different things, right? It's your CMD instrumentation, your sandbox execution, you may have monitoring agents on a quiet system. And so some companies also do whitelisting of binaries that you can run. More so in a blacklist fashion where you basically say, okay, PowerShell.exe cannot run. But more importantly, defense fingerprints your tools that you bring in on the host. And so let's see how we can actually start solving this issue, being on the host, how we can become less detectable and more agile in our tooling, right, that we bring in. And so before we go into retooling, strategic disadvantage for the red teamer on the host is that, well, we talked about you have to move first, right? You're the fence, you have to move first. You need to collect the information, and you may burn your presence. Your presence may get discovered right away. So the way offensive operators move is a little bit more predictable, right? A specific thing that you need to collect from the host to be able to continue persistence on that host. So a lot of unknowns. The problem with bringing already existing tools on a host is just that, right? Is detection. And so how do we make sure we can retool what we have in the field right on the live host? So there was this idea that we may start doing building blocks of things right on the box instead of bringing static tools in. And maybe we can even start building tools that build tools that will be will be part of our offensive arsenal. And also one of the other things that we need to keep in mind while we're doing it is utilization. We have to operate within the realm of what's available on that host, and it may not necessarily be what you want to be on a host. So retooling in the field has advantages, right? You create custom stuff, you create custom code, you blend into the environment, but you also have disadvantages. You have dev time on the live host while being watched many times, and it's a live system, right? So you do not know how the system responds. Your operational security also has to be a priority. So in reality, you've got bugs, you have defensive mechanisms that watch over you, and live offensive dev right on the host is fairly hard. So if we agree with the premise that we actually need to do live retooling on the host, what do we need for this? Let's define some goals. Strategic goals of the recon, let's say, right? The first path in before we go further. You need to stay under the radar for a longer time, survivability. You need to better deliver your code or payloads to the existing ecosystem without changing it. And you need to be able to retool for the unknown, right? You may not know what kind of defenses you have. So from the tactical traits, what does live tooling really mean? So you have to support the transfer of the payloads. You have to support building of those payloads on site while you're evading operating system and sometimes network defenses. So essentially, stop being the kitchen in the the elephant in the kitchen and breaking all the rules while you're doing your recon. Once we agree to that, we start building this, right? What are the properties that we need to accomplish our goals that we set out to accomplish? So from the technical standpoint, you want to avoid logs, right, on the operating system facilities. You may need to get to a reasonable interface with legacy or unmanaged layer, right, of the operating system. You may have a decent interop with OS and APIs that exist on that machine. And obviously, you always need to keep your operational security for your tools. So there's this concept of slim payload delivery, right? So you've got a slim cradle that doesn't pose any threat to the operating system. It's not detectable. It doesn't carry payloads. It doesn't have a malicious feature. It doesn't serve malicious goals. So it is benign from the scanning perspective, right? But it can dynamically load other payloads that you bring in. And you can actually you should be able to load assemblies if we're talking about .NET. And the concept of treating code as data that you bring in into the environment and then you start operating on. The more important things we're going to see down in the presentation would be, so we're going to do compilation, obviously, but we also want to decouple the compilation from the actual execution, right? So the cycle may confuse defense a little bit more. So what are the current options that we have? Well, normally we default to PowerShell, right? It's available, it's installed, it's used very heavily from both defensive and offensive perspectives. We've got WMI, and we also have comma and unmanaged code, right? You can code towards direct API in the Windows machine. You also have direct managed code, which is .NET. Everybody loves and knows about, right? So all of these options have pros and cons. So you're talking about availability of the compilers on the target system, ease of use and logging, for example, for PowerShell through automation API. And then if you want to drop into interop and actually talk to the operating system at the low level, then you have those interfaces and COM that you need to make sure that you actually cover. So, and it also comes down to how well you can actually develop in a live environment there. Okay, so out of all these options, I'm very interested in .NET, right, the managed code, what we can do with it. So the issue of executing code through .NET is not new. There are tons of tools, static tools that exist that should be able to do any kind of invocation of operating system commands to PowerShell from .NET. But our goal here is how do we use .NET into retooling of our arsenal right on the box without having static tools in. So the advantage of the .NET for using this is you obviously have breadth of interfaces to the operating system. Wealth of very well developed, features that target anything from network communication to host communication. You can reach deep into operating system with process invocation or platform invoke. And you have utilization properties to .NET, meaning it is available on at least latest Windows machines. It's fairly flexible, and to solve our problem initially is that it's not logged at the API level, at least for now, right? If PowerShell is logged, then .NET is not logged right now. But it does have disadvantages, and those disadvantages are something that we have to deal with. Well, first of all, it's a slower dev time, right? You have to go through the cycle of writing, compiling, running, writing, compiling, running. There's very little prototyping in .NET inherent to the box, right? We're taking it as carte blanche. There's nothing installed on the Windows machine except for .NET and maybe a compiler. And it is compilation, right? It is identifiable by digital forensics as well. Okay, so we know that we can target advantages. All the advantages are playing towards our favor. But our disadvantages have to be also recognized. So let's address them. So let's start to gradually design and build this sort of prototype, the managed execution toolkit. Behind those big words, what that really means is that using .NET to be able to execute your code, execute your data that you bring in from the outside or write directly on the box. And so we begin with a module of the Typhoon, which is the name for Managed Execution Kit. Proof of concept here is Seesaw. Seesaw meaning really just focusing on C# implementation of that. So when we start thinking about this compilation and running cycle that you rinse and repeat, right? We have a source code, we've got a compiler, you've got the executable, and then you go with it. From the offensive perspective, what is .NET in a nutshell, right? You've got the APIs, You've got the common language runtime, which is the framework of .NET, and you've got compilers that is inherent to Windows installation. But you also have some distant relatives of that, right? You've got code, object model, and you've got some other things that we're going to talk about. So we want to focus on things that build things for us. So code DOM is essentially solving the issue of dynamic compilation and creation of code, generation of code from code, right? You see this from ASP.NET, XML, bunch of UI code wizards in Visual Studio, and it's a solved problem, right? You want to create your code from the code that you have, and you essentially compile something that something from you take a maybe a string of code, right, and you turn it into an object. And so you emit the code, right? Emission of the code is the goal here. And the good thing about this code DOM is that you can do dynamic compilation. No longer you need to invoke csc.exe, for example, right? Because it may be blacklisted or maybe logged somehow from the command shell, so you can actually do it right in the cradle, that slim cradle. You can dynamically compile it. So the first order of operation to solve our issues is REPL, right? Some things that we're missing in .NET, let's do a little REPL so we can constantly, proof our code, prototype our code. You can use VB, JavaScript, or JScript rather, or C# in code DOM. So we're going to concentrate on C#. So we want quick gains, because if we want to see what this machine is about, we need to go into the cycle really fast, and we want to execute interactive commands maybe on it, right? So we're going to take the code, we're going to compile it into some form of a digestible format, and then we're going to try to execute this. So from the evasion perspective, red teams gain, you move away from csc.exe or MS build into the dynamic compilation right at the code level. So what's needed? It's not really hard to compile it, but you need to make sure you take care of certain things. First of all, you need to load your, you need to understand how you want to compile it in a safe manner, right? Do you want to compile it in memory? Do you want to compile and drop the executable on a disk? Where are your temp files are going to be stored? And what are the compiler parameters that you're going to pass to the compiler to accomplish your goal, specifically for REPL, right? And so many things can go wrong here, and let's dive in and unpack what can go wrong and how we can actually do this. So there are certain things that can be evaded while you're compiling in code DOM, right? The detection. So for example, if blue team is detecting DLL drops on the file system, then you can just replace DLLs with TMPs, because .NET has a property of not requiring you to compile to a DLL name, right? It will happily take the TMP name, so that's your evasion point right there. So what is the goal for our seesaw, right, beyond REPL? Is the dynamic combination of C# code, is the dynamic loading of assemblies into memory and removing those disk artifacts that we may potentially have here, right, if we decide to dump a temp file somewhere. And then possibly forcing .NET to compile and run in separate direction, right, for even further confusion of the defense, because if the sandbox looks at the compilation and invocation in one stage, then you may get to the point where they can actually trace it better. And then other things that we want to achieve from the operation security perspective and features that we want in here. So let's go through this one by one. So REPL is still on our list, right? So let's, how do we do this? So we know we can generate code for code DOM, right? We want to have some form of a contract with our code that executes in the loop, right? For example, we want to compile it, we want to get results from it, and we want to dispose the object that you've just run so you don't leak memory or whatever the case may be here. So for code DOM, it's just a string, right? So you put a snippet directives, like for example, using system, into one object or part of the code, then you have some form of an instrumentation from your Cradle code to run the code through dynamic compile, and then you dispose that, right? So we marry code DOM to the compilation. Also, evasion points here that you generate half of the code from the tool, and the other half of the code comes from the operator, somebody who wants to run the code in the REPL. Once you compile, you can reflectively load your namespace. For example, it's called dynamic compile, right? And then you use activator reflection to create an instance of your code that you've just compiled through REPL. Then you get results, and then you dispose. So essentially, this is how our REPL is going to work. And so at the REPL, at the whatever interpreter shell that you have, you specify a directive that goes into preamble, right? And then you have the code, and then you start compiling, and you get the result because you've invoked that the contract. So in this contrived example, we just get the number of what languages and compilers are available on the system, but your mileage may vary. You can start querying the system through .NET. So CS REPL has a code cradle, like we saw. It uses code DOM, right? And it has rudimentary reusable component because of the contract. But it's also sequential. It's also, there's no abstraction. You can run functions off of it. You can create namespaces. You can do any sort of object manipulation beyond your direct branch. So you can't reuse the code. And so it's quick and dirty. It works, but we can do better. To the right side, there is a script that you can actually paste into the REPL right here, right? And so if you brought a script, then you can just paste those things in, and it will compile and give you a result. But so it's a crude way of doing the REPL and scripting together. So we can do better, as we said. All right, let's fix the issue that we had with REPL of reusability and just expansion. Let's create CSX extensions. CSX is just a name. It's a C# extension. That's how I named it, right? So we create a better contract. So we say a pre-launch, run code, and post-launch. Pretty simple, right? But it also maintains that evasion vector, right? So you can actually you can split your code. If somebody's looking in your memory for a payload code, be it a shell code or whatever the case may be, then they don't see it in one buffer. They see it in something that is split between the tool and you, the operator. So we want to create full branching in classes. We want to do compilation as we did before, and we can write extensions that can actually execute real code. This is the example of the contract where we create a namespace. Let's say it's a file that you want to invoke, a code, right? A text file that you somehow introduce into Typhoon, and it has to follow some rules, right? It has to have a specific namespace, it has to have a specific before-after hook, and it has to have some form of execution, your logic and whatever the case may be. So from the operator perspective, they will see an executable, which is a slim cradle that doesn't have much. That is going to load just a code file, right? Clipboard manager.cs, which is a code file. It's not executable. It's not assembly, so it's pretty much safer, right? We're talking about code as data. You bring in code inside, and you start compiling, or write the code inside and start compiling. So we know that CSC or code DOM creates temporary files, or can create temporary files. So after this invocation of compilation, you will have a temp file in your current directory, which is bad for your artifacts, right, for hiding from incident response. We'll address that problem later, but here's the example of what you would do to compile it in one iteration to a DLL, and then you would execute that DLL by loading that DLL into the memory of the cradle, and then you would call that namespace and an object to execute your logic there, right? So we're decoupling compilation and execution goals in two. So talking about DFIR again, right? So some things are good, some things are not. So we're not invoking csc.exe, which is good. but it is still indirectly invoked, right? If you look at the sysmon or a process monitor, you will see that exactly the same facilities are engaged, just not directly from the command line. Also, the other things that we need to we need to make sure we take care of is the temp files, right? They can be transient or permanent, right? So compilation in memory in .NET is a misnomer. It never compiles in memory. It just compiles to a temporary space on disk, right? And so something from the forensic perspective, people are aware, and we should be aware of as offensive operators of that as well. So we're going to deal with this issues, in a different iteration, and we also want to make sure that we can actually load and unload assemblies that we compile and create dynamically. For example, if you brought in some code, you've compiled it, you load it up, the assembly is locked, right, until the end of the iteration or execution of the code. So you can't really, in classic.NET, you cannot remove that DLL from the disk. And sometimes you want to do this because you want to stay in memory. Even if you drop the DLL temporarily for just a sub-second, right, you want to be able to remove it. Okay, so as we talked about, the generation in memory is not really in memory. It still drops it into a temp file. The question is where it drops it, right? It either drops it into a local temp, or it drops it into a local directory, depending on how you compile. So selection of parameters to your CSC and code DOM are very important. This is the example of process monitor that is looking at code DOM compilation and invocation. It's littered with artifacts, it's littered with temp files, it's littered with DLLs that are dropped on the box. We want to fix this. So the next goal for Seesaw is to remove artifacts, right? In order for us to do this, we need to understand limitations of the .NET. First of all, you can't load bytecode. You can't load a stream of bytes or stream of generated assembly into the memory and execute it in the classic .NET without further instrumentation. And so the way to do this is to say, okay, I would like to remove a DLL from the disk, but I'm not able to do so because I'm locked, right? So we have to fix this issue right here. And the way to do this is to bring in the concept of application domains, right? You load your DLL, you load your artifact, you load your executable payload into a completely different application domain from your cradle. You do your job, then you remove it, right? And then you offload the application domain, because now your cradle runs in one application domain and your payload runs in another. You're able to break that coupling, right? And deal with the artifacts. Okay, so we fixed this issue. The other issue that we face as an operator on the box is .NET does not have everything, right? Sometimes you need to run into things and invoke operating system facilities through the Windows API. And here's the interrupt, right? Interrupt is a technique, a set of APIs for .NET to be able to drop down to the operating system level, to the Windows API, to COM, to COM+, to C++, and to ActiveX. And so if CLR is managed code, where we've been living for a very long time while we're creating this prototype, right? Managed code and interrupt to the unmanaged code and interrupt to the unmanaged code is outside of CLR. There is a specific namespace, system.runtime.interrupt services, that takes care of this. And there's wealth of information on the internet. Here's the link where you can get more info, but essentially, and I have to say that that also carries evasion mechanisms, right? Because now you're leaving .NET, which might potentially get instrumented at some point, and you're actually dropping into operating system level. And so what happens is, while you may still be flagged on a payload, your analysis mechanism or workflow is decoupled, right? You're going from .NET to completely unmanaged code, which breaks a lot of workflows in defense. So interrupt essentially works on the DLL import attribute, right? To to your function. You instrument it in such a way that says, okay, that's an external code somewhere over there. After we compile, we'll be able to manage it at the runtime. And so, for example, in this case, we will find a window and we will set the Windows title, right? And we're going to involve a user32.dll, which is hopefully available everywhere, and drive our code from there. So that's a platform invoke, right? That's a shim. And then we can start a process and we can say, from our cradle, we can say, okay, well, I want to find window, which will be found in user32.dll, and I want to set a window set a window title on it. Again, the shim and the evoking code is in different assemblies, or can be in different assemblies, and that plays towards our evasion mechanism. Now, but we can do even better, right? We can do dynamic interrupt. What does dynamic interrupt mean? In .NET 4.0, I believe, they introduced a concept of dynamic object, meaning that the object type is not known at the compilation time. It's given a marker that will be resolved, or a tag that will be resolved at the runtime. And so you can reflectively start loading any DLL that you have on the system directly, not knowing what type of the function you're going to be invoking, or what returns it has, or whatever the case may be. You use some reflection and emit APIs like define type, create type, and get method, which is really helpful, right, and very powerful in our case. So the example of that in our REPL will be to load our system and then load our namespace for dynamic load, which we already know how to do with code dump. And then we just say, okay, well, let's load any Win API, right? In this case, it's user32, and let's call any function from that DLL or assembly. For example, in this case, it's message box, right? And it's all dynamic. So in this case, you move away from knowing what you're going to do at the compile time to knowing what you're going to do at the runtime. So you got yourself a scriptable .NET API bridge, which is really powerful for our purposes. Okay. So by now, we pretty much took care of the seesaw goals, right? We are able to dynamically compile the C# code in REPL. We can do this without, logging for the most part, if we can assume that typhoon.exes can be lodged, whatever. Right, we can load and unload assemblies into memory. We can take care of the artifacts on the system. We can remove DLLs once you load them. And we can do interrupt with code outside of the CLR, okay? But it's still .NET, it's still compilable, right? So can we do something better? Can we do more flexible solution? Can we gain more scriptability out of it? Can we even forgo app domains altogether because they're hard to work with? And can we actually avoid compilation, right? And so, again, let's start building this managed execution toolkit even further, right? So let's look at a component called Delirium, right? So we want to bring in dynamic DLR into the mix and start working with this. So what is DLR, right? In .NET, you've got CLR, a common language runtime, but you also have a dynamic language runtime. A dynamic language runtime, it's a set of services to create dynamic languages in .NET or using .NET facilities. And so the advantage of that is that you move away from statically typed languages like C#, right, where you have to know the type of the variable or whatever the case may be, or object, right, or know the library that you're going to invoke, into something that is completely dynamic, right? Dynamic languages, we know it's JavaScript, PHP, Python, and so it is going to gain us a lot of advantages. Well, from the developer perspective, DLR is used for porting dynamic languages to .NET. So for example, if you want to have Ruby.NET or if you want to have Python.NET, it's all achievable now with DLR, right? And so just like Java virtual machine has, Parrot or Jython or whatever the case may be, the same thing happens in .NET ecosystem, so you can actually work in your preferred language of choice just using .NET facilities. And so it is on top of the CLR. It's a feature or part of the framework, and then you start building your languages on top of it. Essentially, for us, this is the gain, right? We move from this completely focused and managed workflow of knowing your type to something that you're used to do in any dynamic language. You just have an option, object or a variable, and just set some property on the variable directly without knowing what type it is. So to get to Delirium, you have to use 3 assemblies, right? You have to use Microsoft scripting namespace, you have to use Microsoft Dynamic namespace, and then you have to use a namespace and a library of the language that has already been created and ported to .NET. For example, Iron Python, right, or Ruby. In this case, we're going to be talking just about Iron Python, but the rules stay either way, right? And so a pretty powerful thing because we can move away from strong type to dynamic, and we can actually do more code reflection. To us, code reflection means evasion. So in C Sharp, your static types, let's just give you an example. A very common scenario where you need to get something from, while you're on the box, you need to get something from the internet, from your point of presence, like a payload or whatever the case may be. And so in this example, you're getting content of google.com in C Sharp, right? PowerShell is a little bit more dynamic, and so it can create an object of .NET, and then it's not going to be strongly typed, it's going to be dynamic, and you can get exactly the same thing in, with less pain, no compilation, and good things. But PowerShell is logged. So Python itself is it's good for offense because it has a lot of facilities that have been used over the years, right? It has a lot of libraries, and so we can accomplish exactly the same thing with Python, but not having the C Python executable on the box at all, right? So in a regular C Python, you use a library like URL lib2, you fetch the content, and then off you go. In DLR, you're doing exactly what PowerShell does. You're invoking, or you're leveraging .NET namespace to bring in an object, and then you call a property or a method on that object to do something with it, right? All that lives in the ironpython.dll. So what really just happened here from a strategic standpoint, once you run this code, right, and let's say you have set up your IronPython environment through the cradles that we're going to see how we're going to do this. We do compilation watch on the process monitor, and it's empty, right? No csc.exe, no artifacts, no temporary files, and no app domains, right? It's fairly clean, while we're still executing what we want to execute. It's pretty powerful stuff. So, all right, we proved that. So what do we want to do with this? Well, we want to solve exactly the same thing we want to solve with Seesaw. We want to have the full leverage of DLR to compensate for partial deficiencies while managing the .NET advantages. We want to compile Python to EXEs or DLLs if you want to through the dynamic language runtime without artifacts. We want to actually use the features of .NET that were hidden through the regular C# invocation, is to actually load DLLs and assemblies through the byte stream, read network stream, or maybe a pipe, right, or a socket, whatever the case may be. And we want to maintain the interrupt to the native interface through DLR. Okay, so here comes Delirium. It is specifically IronPython. It does work with dynamic types. It mixes and matches styles of programming for Python and .NET, so you can actually have, we'll see examples of that, but you can actually confuse the defense even more, and you can actually reflect code from one language to another. For example, you can invoke C# compilation from Python or Python invocation from C#. So IronPython lives in CLR namespace. Nothing more, nothing less. You import CLR, into your Delirium and REPL, right? And you're done. With Iron Python comes a lot of libraries or a lot of support are actually inherent there, right? You've got Socket, even though you have a .NET counterparty for the Socket, you also have an overlay from a Python perspective. You've got math libraries, you have zip libraries, you've got a lot of good stuff. But please remember that you do not have standard library. You do not have all the other goodies like URL-lib that resides in that small little ironpython.dll. You could potentially load it from a disk somewhere. And here's another evasion point. For example, in order for you to load a standard library for IronPython, it just needs to find the file. It doesn't have to be .dll or .zip. It can be .docx, right? So you can bring in a corrupted docx into the environment and load it up as a standard library, and off you go. So here's the example of how you would actually load standard library if you want to. You can do without it, right? Because you have .NET. So DLR is nothing more than just a .NET technique. It's a heavily reflected, heavily dynamic loaded, introspected way of dealing with a .NET API. You just add reference to the, let's say, Windows forms, and then you call that form, right? Or for example, if you want to import a message box from the form, and then you invoke the a method in the message box, or whatever the case may be. Plus, on top of it, you have the flexibility of the Python, and you can just go off to create a very powerful and fast code. And so other things that you can do with Delirium for now is that if you have a Python code, remember we talk about code as data. We bring in data. It's plain text, right? Nobody knows what we're bringing. It's not executable. It's not detectable. And then you can actually compile Python into DLL if you want to, and load it by other tools. So again, you break the chain of analysis from compilation to invocation across highly reflective pipeline. So you're compiling a module, test.py into test.dll, right? And then you invoke that. And so you can go in even further. Why not just create a Delirium executable that will call dynamic Python files? So for example, you have an extension. We saw the extension that we can create in C#, but we can also create extensions in Python now because it's still .NET. It can still go against that contract that we created, the pre-launch, execute, post-launch, and then we can specify what executable we want, what platform we want, and whether it's a DLL or an executable. Things to keep in mind is that compilation is not runtime as far as dependencies are concerned. So if you can compile things, because everything is dynamic, the compiler doesn't know or doesn't care what you compile. It says, okay, well, let's just throw it to the runtime, right? We're going to compile, give you a fully valid executable, but then at the runtime, you're going to have to figure out a way to meet those dependencies. And so separation of things, you can compile it on one machine, bring it over, and then supplement the runtime with dynamic link libraries like IronPython and Microsoft Dynamic Scripting. So when the defense looks at a payload DLL that was created, or a payload EXEs that is created, that is devoid of IronPython, devoid of Microsoft Dynamic DLL, it doesn't have Microsoft Scripting DLL, it's safe. It's only when they two meet, right, the magic happens. Again, let's do even easier REPL, right? You don't have to compile anything. You can just start working with CLR namespace. Pretty easy, right? You just load it up, and then you execute it into REPL. Here's another example that you can actually go in further, and instead of using the .NET, you can use C types for types of things that you want to call on, interop emulation. But for that, you do need the standard library, but you can still call kernel 32 get Windows directory, whatever the case may be. So this bridge scripting bridge that you've just created gets even more powerful, right? Because now you can actually dump into you can dump dependency on platform invoke, and you can work with C types if you want to. So strategically, what just happened, right? We're all this time we're bringing code as payload to execute in an empty cradle, right? We do not bring compiled code. We do not bring executables. We bring code in plain text format, and then we start running from it, through either compilation in the case of Seesaw, or Delirium doesn't even have compilation, right? You just kind of run it. So on the point of delivery of code, how do you get ironpython.dll into your system? Well, or for that matter, how do you get, maybe there is a way to have an intermediate language construct that you can bring in. For example, if you don't want to bring code to compile, you can split the DLL into two parts, right? Called modules, for example. And the way modules work in .NET is that it's the module is a DLL, but it doesn't have a manifest. So when the defense looks at it, they look at a binary blob that is not executable, that is not, it's nothing, it's just binary blob. But when you combine that with manifest, that's when you get to the assembly. So on that topic, Typhoon itself, it brings in ironpython.dll as an embedded resource in itself, right? So we basically hook assembly resolution when we're saying, okay, well, load me up a Python runtime, and then that hook goes and resolves it to the embedded assembly inside of the Typhoon, right? It just says, okay, well, let's load it from the resource. So that's really good. You don't need to go out and grab it from anywhere. It comes with the tool itself. There are other evasion mechanisms that you can start thinking about, like, for example, that net module that we talked about, and we're going to see an example of that. You can also hide both assemblies and net modules into the downloaded directory for assemblies that you fetch from code itself. It's kind of convoluted, but the way it kind of works is this. Essentially, every executable can have executable.exe.config file, and then you can specify dependencies where to fetch additional DLLs from, right? And so you can hide ironpython.dll if you cannot bring it as an internal resource to fetch it at the runtime. So for net modules, this is the example of what a Microsoft intermediate language looks when you're compiling net modules, right? It's just a just an assembly without manifest. And so this brings us to a point of, well, can we even compile dynamic net module from C sharp into an assembly through the DLR? Yes, right? We can say, okay, well, let's stage code into a string. Like, for example, it's going to be a interrupt shim in C sharp, right? You see the DLL import for a bunch of libraries on the operating system. And then what we're going to do, we're going to generate library through Python. We're going to stuff it into a variable, all in memory. We're going to create a list of those libraries that we've generated. And then we're going to be reflectively loading them in memory, again compiling them together to create a third dynamic assembly, right? And then calling an API or a function within this created dynamic assembly to, for the gain, pretty much. So essentially, you're looking at bits and pieces, building blocks that you're bringing into Typhoon, right? And you're compiling them into memory to invoke something that will gain you more visibility or run your code, your payloads, or queries. Okay, so things about hiding things into memory. Like, for example, you could potentially bring in a zip file through the code, right? You can unwrap it into the memory. You can stuff it into a memory mapped file which doesn't have counterpart on the disk, and then invoke payload from that memory mapped file directly, right? That also speaks to the evasion, and it's really, really hard to detect unless every memory mapped file is inspected, or just the fact that you're creating a memory map file is locked or detected and stopped. And so we can even do we can invoke IronPython from IronPython over .NET assembly with variables, right? You can dynamically create, constructs like bring string, and then you say, okay, well, that string is going to be hello world, and then you can create a Python engine. Then you can have a script that you create from that string that you've just, passed to it, and then you can reflectively execute Python code. More stealth, there are some examples here. If you want to do compilation in memory here, you can load the file. You can it just kind of shows you that you can actually go really deep in reflection, and the more reflection you have, the less chances of that workflow for folks on the defense side who do not know what to look for. They will just not be able to put two and two together to be able to detect that, right? Or at least part of it. Okay, so we've done recon, right? You can do WMI query and everything that .NET can do. Can you do exploitation through that? Okay, so shellcode is a shellcode, right? It can be a binary blob, or it can be a text blob. And that payload follows exactly the same strategy, right? Code is data. You bring shellcode in plain text form and introduce that into the cradle that either compiles it and then runs it, or just runs it directly through reflection, right? You can create, compilation with unsafe keyword, which means you're lowering the guard for .NET to say, I'm gonna check for memory leaks or whatever the case may be, and you say, no, I know what I'm doing. Just give me direct access to the memory, right? So that's what .NET does, and then you essentially say, okay, well, again, you can say memory map file. You can stuff your shellcode in the memory map file, reach out to the memory map file, and map a pointer to the location of the memory mapped file where your shellcode is, and off you go, right? I mean, there are issues with virtual alloc, and some things may not work, but in concept, you should be able to do that. Okay, so from the seesaw style, you can create a C# style shellcode, which may be dynamic because you're bringing stuff in, right? And that's how you would pair it up with, let's say, Metasploit, where you would create a a listener to a specific C# shellcode connection, and then you create the thread, and then you do this, right? Pretty standard. But from Delirium standpoint, you can do it in Python too. Like the buffer that contains the shellcode may be just like any buffer you're doing in regular C Python, right? You just stuck it in a buffer, and then you have a socket, and you can send to it, right? Socket comes with IronPython.dll. You do not need to have standard library, while you're still using the .NET and not having a single Python executable that is a true Windows executable on the system. And then if you're missing something, you can always drop to PowerShell, right? You can always start a process. You can start a process with encoded commands, and essentially the path is known how to operate PowerShell here. So for development, Python is relatively easy, right? If you abstract from the fact that you're still working with .NET and you still work within namespaces, and some of them may not necessarily be exactly the same as in a regular Python, but your lists are the same, your enumerables are the same, your lambdas even are the same, so you can write pretty reflective code here and pretty concise code to accomplish your goals. And everything, again, starts with importing CLR and then importing your namespaces, just like in a regular C# or VB script. So Delirium Typhoon's goals are met, right? We're able to leverage DLR to avoid PowerShell together while gaining scriptability, while defeating much of the artifacts that C# generates on the box, or csc.exe generates on the box. And we can mix and match, right? We can drop to .NET from Python, or we can use Python purely for our goals, socket connections versus, system.net, whatever, right? And then we can do fully reflected code, and we can, if not remediate, then at least force analysis into that stage where they need to work a lot harder to figure out the ins and outs of our code here. So Typhoon Managed Execution Toolkit has two parts for now, right? It's the seesaw that is able to do the REPL, do the dynamic deletion of artifacts, do compilation of the DLL, loading the DLL directly without executables in memory, and calling functions in that DLL. And you also have a delirium part, right, which forgoes compilation altogether, but brings in RN Python DLL and then works on a DLR to be able to execute code directly without compilation, and then compile code to XCs, DLLs, load them up exactly as Seesaw did, and also speed up the development maybe 2 to 4 times, right live on the host. So essentially, this brings us to the point where our goal of live retooling can be actually realized and can be achieved, right? And so you do have a disadvantage, a first mover disadvantage, because you need to be able to go and query the system. But you can do this in a little bit safer manner by using the .NET facilities and by correctly invoking compilation, correctly watching over your artifacts, or bringing in your dependencies as in Python DLR, and then that makes your operational security as an offensive operator much stronger, and that makes you think what you're actually doing on the box and how that affects your path there. So the code is out there. It's released. It is really alpha, right? I mean, it's working, but it's definitely not at the point where it's super uber performant or whatnot, right? And essentially, if I can actually drop to, I don't think I can drop to this guy. So I can drop to my VM. I don't know, but yeah, the code is there. The examples are there. If you guys want to download, play with it, or contribute to it, obviously, I'm very much open to that. And if you have any questions, let me know. Thank you.